Okay, good afternoon. Welcome to Emergent States of Matter, Wednesday, March the 31st. So today we're going to talk about superconductivity. So we haven't yet talked about that. So I'm not sure what section this is in the course, since I've lost track of the numbering. So in my notes, this would be 4.10 on the Ginzburg-Landau theory of superconductivity. So what I'm going to do, though, is I'm going to go right back to the beginning of the course material that I skipped at the beginning, and this was in section 1.3. Basic features of superconductors. So what I propose to do is this. I want to just give you some very quick outline of the main ideas of superconductivity. And then once we've done that, we're going to, as I said, sometime through the end of today's lecture, get to the Ginzburg-Landau theory of superconductivity, which is a description of superconductivity, which is very similar to the Ginzburg, to the Gross-Pitievsky equation that you've been using in the last lecture to describe superfluidity. So the logic that I want you to think about the logic. The logic that I want you to think about is the following. So in superfluids, what we saw was the following. We started off with some basic, just what were the phenomena. And then we came up with a two-fluid model. And then we didn't really, that was purely phenomenological, but at least it gave us some way to start thinking about things. It was a kind of low velocity model of the system. And then what we did was we made a microscopic model of weakly interacting bosons. And from that weakly interacting model, we were able to recover many of the features that we'd seen in the phenomena in the two-fluid model. We could see that there would be, off diagonal long-range order. We could see that there would be quantum vortices. We could calculate the sound waves. We could see that there'd be second sound. We could see that there were the excitation spectrum. So we were able to understand a lot of those things. And then, but that was quite complicated and required us to do a fair amount of, field theory and so on. So then we made a macroscopic model, which we had derived from our Hamiltonian of the microscopic model. So that was the Gross-Pitievsky equation. And in the homework, you will see how from this macroscopic model one can derive the excitation spectrum and make essentially an equivalent theoretical description of a superfluid, but now never really worrying too much about the small scale behavior. And this microscopic model that we had built, we used pseudo-potential ideas. So we had explicitly done some kind of coarse graining and looking at long wavelength phenomena. And so what we're doing in the Gross-Pitievsky equation is taking that to its logical extreme, where we simply don't even start off with a microscopic model. We just we'll start off with something that is macroscopic. Now, what I want to do in superconductivity is the analog of this. So I want to now talk about the phenomena, and that's what we'll do in a few minutes when we finish the introduction. And then we're going to bypass the two-fluid model. So there is a two-fluid model of superconductivity, but we're not going to talk about it. The microscopic model of weakly interacting bosons, the analog of that is what you're doing in the homework from this week and from for the next week as well. So this is the BCS theory of let's say emergent bosons. And that theory is very good at describing certain aspects of superconductivity, as I'll show you in a little while. And then the next thing that one can then do is ask for a macroscopic model. And in the case of superconductivity, that's known as the Ginzburg-Landau theory. And so what we'll do is we will explicitly start off by using that description. So the BCS theory I'm not going to cover in class, but I will talk a little bit about the relationship that it has to the to this sort of logic. So let me give you now an even sort of even more bird's eye view of the logic. So what I want to do is write down what I regard as the most fundamental aspect of superconductivity, which is the spontaneous breaking of gauge invariance, and I'll show you how that is connected to everything. So let's put here in the middle the BCS theory. And what this is it's a many body theory of Cooper pairs. So as I told you at the beginning of the course, where electrons form a pair, and then those composite bosons then can do something like Bose-Einstein condensation. But now you're sophisticated enough to know that Bose-Einstein condensation is not literally just ideal bosons, but can be weakly interacting bosons as well. And in BCS theory, it's really a theory exactly like that. So it's basically using what we did in superfluidity for superconductivity. So BCS theory does that. And what BCS theory allows you to compute in particular is the thermodynamics. So we'll talk, I'll tell you a little bit about the thermodynamics of superconductors in a few minutes, but the most important thing is that there's evidence for an energy gap, and what the BCS theory is able to provide for us is the understanding of where that energy gap comes from. And that is the subject of the next homework exercise. Now, before you get to the BCS theory, of course you start off with a description of a Fermi liquid or normal metal. So over here, you can say that you have the normal state of superconductor. And so that normal state in very elementary stat mech or solid state physics classes, you've used the idea that this is a an ideal gas or free electron gas inside a metal. In the more sophisticated way to think about it is as a Fermi liquid. Where the electrons, the free electrons, are not electrons at all, but they are quasi-particles in the same sense of the quasi-particles that we described in the theory of superfluids. So this normal state is a Fermi liquid, and what you can show is that that Fermi liquid undergoes an instability to forming Cooper pairs. So this is unstable. In fact, I'm going to make my box a bit bigger. And so that instability is something that we will describe a little bit later in the course. That will be, if we have time to do it, another homework exercise. And so that instability is the thing that causes the superconducting state. And historically, what happened was in 1956, Leon Cooper, who was a postdoc with John Bardeen, understood that if I take 2 electrons above the Fermi surface of a regular sort of free electron gas, if you will, or quasi-particle gas, under certain circumstances, it can form a certain kind of bound state. And that was the idea that you can form a Cooper pair. And so we'll talk about that. And then what the BCS theory did was generalize this to not just a single Cooper pair, but to the many body theory of interacting Cooper pairs. And in a sense, that's easy for you to do without any thought using the techniques that I've shown you. Now, what the BCS theory allows you to do is exactly as we talked about on the previous blackboard. It allows you to derive a macroscopic description, which is the Ginzburg-Landau theory. So I'm going to put over here Ginzburg-Landau theory. And that is derivable from BCS theory, and that was done by Gorkov in 1959, looking at the long wavelength limit, literally coarse graining the Green's functions for BCS theory. Now, we're not going to do anything sophisticated like that in this course. We're going to simply use phenomenology to write down the form of Ginzburg-Landau theory. So you can derive this by a derivation from Green's functions. For those of you who went to my course on statistical mechanics, know that derivations of coarse-grained theories from microscopic theories are not really terribly satisfactory. And let me explain to you why. So when you write down BCS theory, of course, this theory has a limitation. And in the case of superconductivity, that limitation is that this is for a weak coupling superconductor. Just like we talked about the weakly interacting Bose gas, so the BCS theory is, if you like, the superconductivity analog of that. And so it is what we say is weak coupling. There's a very weak interactions built into the model, the weak Cooper pair interactions. So if you derive something from Green's functions from a weak coupling theory, then the derivation is only valid in weak coupling. But in fact, the Ginzburg-Landau theory can also be derived phenomenologically based on symmetry. And because it can be derived based on symmetry, then you're not restricted by the notion that a weak coupling theory is the source of the theory. So in other words, if I derive Ginzburg-Landau theory from the BCS theory, that is only valid in the weak coupling limit. But in fact, Ginzburg-Landau theory can be understood from the point of view of phenomenology and symmetry, and it's true for any superconductor, not just a weak coupling superconductor. So Ginzburg-Landau theory is in a sense much more general than BCS theory. And in fact, today, we don't understand the microscopic theory of high temperature superconductors, but we do understand the Ginzburg-Landau theory for high temperature superconductors. So everything that I just said has its analog in what I talked about in statistical mechanics. Those of you who went to that class will remember that at the beginning of the class, we talked about the derivation of the Navier-Stokes equations of fluid mechanics from a microscopic theory of particles bouncing around in a box. And what we discussed there was the idea that I can make a kinetic theory of gases with weak interactions, and I can describe the scattering of particles using the formalism invented by Boltzmann, and that extension of kinetic theory of gases to weak interactions enabled me to derive the Navier-Stokes equations, but I could also derive the Navier-Stokes equations in a few lines phenomenologically. And so what I told the class at that time was that this was much better than the microscopic derivation, because the phenomenological derivation was valid for dense liquids, for which the Boltzmann equation of scattering of particles was not valid. That was only valid for low densities or weak interactions. So all in all, what I've just told you is that in physics, we can usually calculate things precisely when interactions are weak, and we can derive the relationship between different levels of description in that way. But the true way to derive those things is based on phenomenology and symmetry, and that is a much more powerful way to get results that are valid outside the weakly interacting regime. Now, what is Landau-Ginzburg theory good for? Well, the thing that you ultimately want to describe in superconductivity is the electrodynamics. So the thing that gives superconductivity its name is that the resistance is equal to 0. And there's another aspect of electrodynamics, which is that the magnetic response. I'm just going to write this down, and I'll explain what I mean by it later in the lecture, and then also things like the Josephson effect. It's really Josephson effects, type II superconductors, and so on and so forth. So all of those go under the heading of the electrodynamics. So let's put that in its own little box over here. And that's the things that we would like to be able to understand. And the great thing about the Ginzburg-Landau theory is that it enables us to understand those things. BCS theory, in fact, is pretty lousy at explaining the electrodynamics of superconductors. In fact, when the BCS theory was written down, it actually gave the wrong result for the electrodynamics. It wasn't gauge invariant, and it really required some extra work done by Phil Anderson in order to understand how to describe the electrodynamics properties of superconductors from the BCS theory. So the thing that I want to put in here is the spontaneous breaking of gauge symmetry. And that goes in here. And that can be understood by combining the so-called random phase approximation with BCS theory, and from that one can understand the electrodynamics. So this is, in some sense, the analog of the off-diagonal long-range order picture of a superfluid, but now to a superfluid that is connected to a gauge field, which is the electromagnetic field. And so this idea of spontaneous breaking of gauge symmetry is also built in to the Ginzburg-Landau theory. So Ginzburg-Landau theory is one way in which one can write that down. And so this is a kind of roadmap, if you will, for the different levels of description. And superconductivity. Okay, so now that we've understood that, what I want to do now is I'm not going to. If this was a course on superconductivity, for example, you'd spend probably several weeks discussing all the microscopic aspects of superconductors using BCS theory, which we're not going to do. We're going to really try to understand in more detail the electrodynamics. And so what we're going to be focusing on is sort of everything above this line here, and the BCS theory is the thing that's left for you for the homework. Okay, so now let's talk about the basic phenomena. And so this is section 1.3. So let's just talk about the history. So this was discovered by Cameron and Onnes's graduate student in 1911. So this was the zero resistance of mercury and tin and so on for temperatures less than a critical temperature, which we'll call TC. And this critical temperature was, typically something like a few Kelvin. Prior to 1987, the highest TC that was known was about 23 Kelvin. So this is the critical temperature. And this critical temperature was TC, was typically order 1 to maybe 20 Kelvin until 1987. So the high temperature superconductors are lanthanum copper barium oxide and later yttrium barium copper oxide. They were discovered, and TC went up to 40 and then up to 90. So that was what was going on. Now you might wonder why was Cameron Onnes looking at the resistance. So the motivation is quite interesting. So what he thought was that the electrons in a solid, electrons in a metal, is equal to some kind of fluid, some kind of liquid. He was right about that. Today we think about Fermi liquids, we think about that, and even one of the hot topics in solid state physics right now, this very year, is the properties of electrons in graphene, where the materials are very pure, there's very little scattering, and so the electrons behave literally like a fluid. And you could start using the Navier-Stokes equations of fluid mechanics to start dealing start describing electrons in materials. So that's a frontier topic of solid-state physics right now, and of course would be a great topic for somebody to write about in their term essay. So electrons in a liquid, electrons in a metal equal a liquid, and so therefore, if you make a temperature low enough, maybe they'll freeze. And if they freeze, then that means that they can't move. And so that means that therefore they should become an insulator. So that was his idea. So of course it was the exact opposite of what he had expected. So so let's have a look at what the data looked like, at least from the point of view of a sort of sketch. So here is the resistance, and then what you see is here's your temperature Tc, and below Tc it literally is 0, and then there's a discontinuity, and then it literally drops like that. And the you know, how do you measure this? Well, you can measure this by setting up persistent currents. So just like we talked about the persistent currents in a superfluid in an annulus geometry, so you can do the same thing in a superconductor. You can make a ring, you can generate a changing magnetic field, and that will create a current in the ring. And then so you measure a persistent current in the ring generated by a changing magnetic field. And then what you do is you turn off the field and you measure the decay. And so what you should expect is that the current will decay. It'll be what it initially was, and then e to the minus the resistance over the inductance times time. That's how a current should decay in a loop, and you can measure this by a torque experiment. I'm not going to go through that in detail, and so what you can measure is that the decay is very small, very slow. And that implies that the resistivity is less than about 10 to the minus 23 ohm centimeters. And that's what I wrote down in my notes. That is almost surely too high. I'm sure there's an even better bound on that. And just for normalization, the resistivity for copper is about 10 to the minus 9 centimeters. So this is really quite a dramatic effect. So that's the superconductivity. Now the next important thing that happened was the discovery of magnetic phenomena. So now let's fast forward to 1933. And let me just write some names in here. So this is Kalman and Onnis. So fast forward to 1933. So here you have what is now known as the Meissner-Ochsenfeld effect. And usually people just call it the Meissner effect. And And what this is, well, this is more actually, actually, I'm going to just change this. I will just say one more thing before I get into the Meissner-Ochsenfeld. So, so the other thing I want to say is that, that magnetic fields can destroy superconductivity. And so if you have an external magnetic field that is greater than a certain amount, then the superconductivity gets destroyed. So you get a phase diagram that looks something like this. So I'm going to call the value on the vertical axis the critical field, HC. So inside here, you have a superconducting state. Outside here, you have a normal state. And then this transition over here is a second order transition. This transition across here is a first order transition. And I will talk a little bit more about the thermodynamics of that in a minute. And roughly speaking, if I want to know what the shape of this curve is, you can approximate this by the following formula, that HC is equal to HC of 0 times 1 minus T over TC squared. So that's a kind of empirical formula for what that shape is. And this HC can be something like 20 Gauss for iridium. TC is 0.14 K. And it can be as high as 2 times 10 cubed Gauss for uranium, whose TC is about 0.6 Kelvin. So so these are some of the material parameters that are important. Now, why is this useful to know? Well, this is useful to know because we can say something very fundamental about the thermodynamics of a superconductor. So the fact that the superconductivity can be destroyed by a magnetic field tells you that the energy of the magnetic field must somehow compensate for the gain in energy when a normal material becomes a superconductor. So the interpretation is this. So that the superconductor is the lowest free energy state of the material, of the metal, when you're below TC. So what must happen is therefore, when we add an external magnetic field, the magnetic energy must compensate for the difference between the energy of the normal state and the energy of the superconducting state. And of course, this is free energy. So let's write that down as an equation. So what that means then is that the that if I have Fn is the free energy per unit volume of the normal state, and Fs is the free energy per unit volume of the superconducting state. And what must happen is that the difference between the free energy of the normal state and the free energy of the superconducting state, that must be equal to a magnetic field energy, and the two states coexist on this phase boundary here, and so that must equal the critical field squared over 8 pi, and this quantity here is the magnetic energy per unit volume from Maxwell's equations. So in other words, once you add the external magnetic field added to the superconducting free energy, then it raises the energy to be higher, and so the state that is the lowest free energy then is the normal state. So this is true on the phase boundary. Okay, so that's the magnetic thermodynamics. So now let's talk a bit more about what happens when you add a magnetic field, and so that's what is section 1.3.1, which is the Meissner effect, the Meissner-Ochsenfeld effect. So this was discovered in 1933, if I remember correctly. And this is the fact that what I want to show you is that a superconductor is not just a superconductor. It actually expels a magnetic field. So let's say a superconductor, that's the abbreviation I'm going to use, is not merely material with infinite conductivity, or zero resistance, zero resistivity, but it also expels magnetic field. And this was only discovered, 20 years after the discovery of superconductivity. So let's ask ourselves, what does Maxwell equations tell us about superconductors? So what do Maxwell's equations have to say about superconductivity? So let's start off with the third or fourth Maxwell equation. So let's start off with this one. Curl E is equal to minus 1 over C dB by dt. And I'm going to be using some hodgepodge mixture of of units from now on. So I'm using Gaussian units, and so I'm using the speed of light is put in here explicitly. So this is an equation from Maxwell's equations. And then the other thing that we know is that the constitutive equation that tells you how the current density is related to the electric field that drives a current. So this is the current density. This is the conductivity. And what we know is that the conductivity is equal to infinity. So in a superconductor, so this is going to be infinity in a superconductor. So in other words, another way of saying that is that it means that we can think of an E is equal to 0 if sigma is equal to infinity. So if E is equal to 0, then what that means is that dB by dt should equal 0 inside a superconductor. And you might say, well, why would that be the case? And the answer is, if I've got a material, so let's draw our superconducting material. So there it is. There's our superconductor inside like this. Well, what it will have is currents that can exist on the surface. So I'm just going to draw them like this. In reality, they're 3D. And those surface currents can also create magnetic fields. And so they were so those currents then are the things that must conspire to make dB by dt equal to 0. So what we've learned then from Maxwell's equations is that we expect that inside a superconductor we would have the relation that dB by dt is equal to 0. So that's what Maxwell tells us. So I'm going to now argue that this isn't correct. And so we can see that by a kind of paradox. So the paradox is this: I'm going to create a final state, and I'm going to assume it's in thermal equilibrium, and we're going to see that that final state will be different depending on how I get there. In other words, I won't be able to get a superconductor at thermal equilibrium if this were the case. So this isn't correct, as we can see by a paradox. In other words, I'm going to now show you that this conclusion Maxwell equations implies that you can't have thermal equilibrium. So let's see how this paradox works. So let me draw the phase diagram of a superconductor again. And when we talk about a superconductor, the phase diagram that's most useful to draw is the temperature external magnetic field axis, like so. So here's our phase diagram. Here is our curve of hc as a function of t. This is the superconducting state, and out here is the normal state. So what I want to consider are two different ways to get to this point inside a superconductor. So we want to look at this point over here, and I want to start over here. So we're going to say start and finish. And in one way, what we're going to do is we're going to go down in temperature to this temperature over here. And then we're going to increase the field and get to the finish point in the phase diagram this way. So that's going to be one way that we do things. And then the other way that we do things is going to be different. What we're going to do instead is we're going to raise the field first up to here, and then we're going to go down in temperature like so. And so this route is what's called field cooled. And this route over here at the bottom is what we'll call zero field cooled. Okay, so let's have a look at what we expect in these two different cases. So I'm going to imagine that I have a circular, or really a cylindrical superconductor. So I'm just going to draw it like this, just because it's easier for me to draw. So I'm going to take my superconductor like so, and this is with an external field H is equal to 0, and then what I've done is I've cooled it down from the starting condition to the sort of intermediate point over here, which I was just drawing it. So there's my picture, and then what I'm going to do is, now that I've got my superconductor like so, now I'm going to add the external magnetic field. And so this external magnetic field is going to produce field lines, which I'm going to sort of draw in a rather crappy way like this. And they don't go inside the superconductor because dB by dt is equal to 0. And so the field lines don't penetrate the superconductor because B dot is equal to 0 in the superconducting state. And so therefore, if B is equal to 0 inside the superconductor, before I apply an external magnetic field, it has to stay 0 when I apply the external field, and so I'm going to get the picture like I've shown you here. So that's what happens when I have the system to be a zero field cooled. So now let's ask what happens when I cool it in the field. So again, here is my material. So now it starts off as being in the normal state, and then I apply an external magnetic field. So it's now in the normal state, but now it has a field going through it. So let's draw in the field. Like so. So now I've got H is non-zero. Here H is equal to 0. Here T is greater than Tc. Here T is greater than Tc. And then now I'm going to cool it down. So now this thing becomes a superconductor, but the external magnetic field stays the same. As it has to do. So now H is non-zero, and now T is less than Tc. And so now my final state is this one. And my final state over here is this one. And you can see that the two final states are not the same. And so in equilibrium, the final state of the system should be independent of the history of the system. And we see that this is not what this it's, but this thought experiment says it isn't. So that's a problem. It's also what is not observed. So in practice, this isn't observed. In practice, we always see so we always see this configuration regardless of the history. And so what we've learned is that, i.e., the field has been expelled. And then for large enough external magnetic fields, the field enters the superconductor and destroys the superconductivity. So that's known as the Meissner effect. So one last comment about the magnetic material, about the magnetic behavior, which is that metals typically have a permeability of about 1. And so what that means is that normally we would write down that B is equal to mu times H. And so that means that in a superconductor, B and H are more or less, most metals, they're more or less interchangeable. Okay, so that's the electrodynamics of a superconductor. So now let's talk about the thermodynamics. So a metal will typically have 2 contributions to the thermodynamics. One that comes from the atoms that make up the lattice of the material, and then the other that comes from the electrons itself. So normal metals and superconductors have 2 principal contributions to the thermodynamics. And what we're going to be mostly focusing on is the specific heat capacity. So one comes from the the atoms in the crystal lattice. And the other comes from the electrons that are mobile and floating around and causing metallic behavior. So what we know is that for normal metals, and again, this is something that most of you know from elementary solid-state physics, the heat capacity can be written in the following form. So at low temperatures, we get these two contributions. So this contribution here, so theta, is the Debye temperature, and this is the part that comes from the lattice of atoms. And in elementary solid-state physics or elementary statistical mechanics classes, you've learned how to derive this heat capacity. Think of this as, if you want to think of this as a quick and dirty way, think of what we did in black body radiation, in statistical mechanics, or even in superfluids. You know that the energy scales as the temperature to the fourth power. That's the Stefan-Boltzmann law. And the same thing is true for phonons in a superfluid. And so when you differentiate to get the heat capacity, you get this cubic power. And then this part over here, so this comes from the electronic heat capacity, the electronic heat capacity. Oh, let me just say what A is. A is 12 pi to the fourth over 5 times n kb, where n is the number of atoms. And then this is the electronic contribution. And this gamma is the thing that you've certainly calculated in elementary statistical mechanics for an ideal gas of fermions. So this is given by this formula in terms of the Fermi temperature, and this would be true for free electrons. And this was first worked out by Sommerfeld in, I don't know, 1927 or something like that. So that's what we expect to happen in a normal metal, and so what you would expect to do if you were an experimentalist and you wanted to plot this, is what you would do is the following: you would plot the temperature squared along the horizontal axis, and on the vertical axis you would plot the heat capacity over temperature, like so. And then what you would expect, if this were true, that the result would be some straight line, like so, and the intercept here would give you gamma, and from the slope you can get the quantity A over theta cubed. So that's what you would expect, and so you can determine these things for a superconductor as well in the normal state. So this would be a metal or a superconductor in the normal state. And so if I write C over T is equal to gamma plus beta T squared, then you can read off gamma and beta. Okay, and this is the thing that we call beta over here. So what happens when H is less than Hc. So this would be true for H greater than Hc. Now let's put on a let's reduce the magnetic field, and let's see what the behavior becomes. So let me try to draw this. So this is what you see when you have a superconductor. So let me explain what's going on here. So the first thing is I'm going to write the superconducting heat capacity as the heat capacity of the electrons in the superconducting state plus the heat capacity of the lattice in the superconducting state. I'm going to assume that the lattice, of course, doesn't change. Then the heat capacity in the normal state is just the heat capacity of the electrons in the normal state plus the heat capacity of the lattice in the normal state, which is the same. And then the heat capacity of the electrons in the normal state, that's just the thing that we called gamma T. And so what that says is that we should expect then from this that Cs minus Cn, the superconducting heat capacity minus the normal capacity over temperature, should equal the electronic heat capacity over temperature plus gamma, like so. And so this is the behavior that you would expect. And so when I draw this dashed line here, this dashed line here represents the heat capacity in the normal state, i.e. H greater than the thermodynamic critical field. And then this orange, this yellow, whatever color this is, this curve here is the behavior of the heat capacity in the superconducting state. So this is a very strange behavior. So you see this discontinuity here. So this is a discontinuity in the heat capacity, and if we have a discontinuity in the heat capacity, so that means that we have a discontinuity. So this is T ds by dt, which is T, and then S is minus df by dt. And so this is this is going like d2 f by dt squared. And so the fact that this is a discontinuity in the second derivative of the free energy, this implies that this transition is a second order phase transition. So this picture that I've drawn, which is the picture as it was known for most superconductors until the late 1980s, is why we say the superconducting transition is a second order transition, because you get this discontinuity in C, and that discontinuity in the heat capacity is what then gives you the order of the transition. So again, as you remember, in elementary statistical mechanics, the order of a phase transition is determined by the discontinuity in which derivative of the free energy is discontinuous. Now, as you probably know, in modern theory of phase transitions, we know that actually you don't just get discontinuities, you get all sorts of other singularities at second order phase transitions. And so this isn't a correct way, that's not the modern view of how to characterize phase transitions, but the name still sticks. And so we call this a second order phase transition. So one of the things that we also find from this is we can extract the electronic heat capacity and what we find is this: if you plot the electronic heat capacity in this way, so normalized by gamma Tc, what you find is that heat capacity follows a straight line. So this is a log curve. So I'm going to erase this. This is not correct. So this is the logarithm. And so what that then tells you is that we've learned from this that the electronic heat capacity at low temperatures has the following functional form. It goes like some number times e to the minus b Tc over T. In other words, it has this sort of activated form. And typically A is order 10, B is of order 1, something like that. So this behavior, this exponential behavior of the heat capacity is interpreted in terms of an energy gap. In other words, this is basically saying that the electronic heat capacity goes as e to the minus some energy gap delta. I'm going to write it as delta 0 over kBT, and that is that is indeed the prediction of what BCS theory predicts. And it's very different from what you would have in the normal state of a metal, where the heat capacity would go linearly to 0. And so in the homework, the one I'm going to distribute later today or tomorrow, in that homework, you will actually derive delta, from the BCS theory. So delta of T is calculated in homework 5. And you'll get to do that. It's a many body effect on the system. So let me just draw a picture of what we're saying about the nature of the excitation spectrum of a superconductor. So essentially, what I'm going to be drawing here is energy in this axis, and so what I want to draw over here is a normal metal. So these are going to be occupied sites, occupied states. So the white line represents the Fermi surface. And then above that is a continuum of states. And that picture is what we would expect for normal metal. And then what we're saying is that if I now have a superconductor, so the superconductor, everything is basically the same. So I have the same thing over here, like so. But now there's an energy gap. So now I have a gap like so, and then I have the excited states up here. And this is what you would get in a superconductor. And this, what? And this distance here is the energy gap, and so that's the picture. And in homework 5, you get to compute the density of states. That this picture is based on. And it may sound complicated, but it's relatively straightforward, and the homework walks you through that. Okay, so I mean, basically so basically, how does this picture explain this exponential behavior? Well, the significance of this energy gap it's sort of like what happens in a semiconductor. You at temperature T, the fraction of electrons which are excited is something like e to the minus delta over kBt. So that's really where all this heat capacity behavior comes from. So again, in the homework, you'll get to derive not just the energy gap, but you'll also get to derive the nature of the quasi-particles and their energy spectrum, and just like we did for the superfluid helium. So this is really quite a beautiful piece of theoretical physics that's within your grasp, and I think that's quite exciting. Okay, so we have 3 minutes left. Let me just talk very quickly about start talking about the notion of type 1 and type 2 superconductors, and then we'll quit for the day. So, so this is in my notes, section 1.3.3, type 1 and type 2 superconductors. So I told you that we were sort of taking a historical perspective, and in 1933 we discovered the Meissner effect. The thermodynamics was known long before then, or sort of after then. But now I want to fast forward to the to 1955. Something like that. And so this is the idea of Abrikosov vortices or Abrikosov flux tubes. So far, what we've talked about is the way in which a superconductor can either be uniformly in a metal or it can be absent from it if it is a superconductor. So what Abrikosov discovered was that under some circumstances, for some superconductors, magnetic flux can enter the superconducting state, but it does so in it does so in a non-uniform way. And in fact, forms a crystal lattice of magnetic flux. And we're going, and this was discovered theoretically. And observed experimentally. And Abrikosov and Ginsburg won the Nobel Prize, and I think they won it the same year that Tony Leggett won it for his work on superfluids, on helium-3. So. So I think we'll talk about this in more detail next time. Okay, so that's where we'll leave things. I'm going to turn off the recording, and then I'll be happy to take any questions.